Okay, and the last example that we want to look at are when your roots generate complex conjugate pairs. So when dealing with complex conjugate roots, there are two options. One is you can use the first method and substitute the complex root in for s. This is done in a lot of textbooks. This is not really an approach that I follow because it's complex number algebra and some people get confused. It's very easy to make a math error, etc. And it doesn't necessarily give you the roots in a form, doesn't give you the expansion in a form that, as we'll find out later on in the future, gives you some physical insight. So that method we won't actually cover in class. The second approach is to use MATLAB and a command called the residue command to find the expanded terms. And the third method is to complete the square, and this is the method that we'll go over in this lecture. So here's an example of a function, and as you can see we have two terms in the denominator, and this term here will not factor into additional real roots because this term has complex conjugate poles. So when we rewrite this, we want to then take the first term, so we'll write it as a over s plus 3. And then the second term we're going to take in its entirety, so we have bs plus c over s squared plus 8s plus 25. And so we're just going to use the algebraic method where we equate powers. So we take the numerator of the left-hand side and the numerator after we get a common denominator on the right-hand side, and so we get this expression shown here. And then multiplying out the terms and collecting, and so that we see the terms of s squared, s, and the constant term, we can then equate coefficients. So if we look at the s squared term, we have 0 is equal to a plus b. The s term will give us 0 is equal to 8a plus 3b plus c. And then finally the constant term gives us 20 on the left-hand side and 25a plus 3c on the right-hand side. So if we do the solution for that, we get a is equal to 2, b is equal to minus 2, and c is equal to minus 10. So we can rewrite that as follows right here. Okay, now what we want to do is, after we have found, so important to find the numbers using the partial fraction expansion first. Now after we have found the numbers using partial fraction expansion, the next thing we want to do is we want to look at this denominator and we want to complete the square. So the easiest thing to do is to take half of this middle term, so that would be 4, and then square it, which would be 16. So this is basically s squared plus 8s plus 16, and then what's left in this 25 is 9. So that s squared plus 8s plus 16 can be rewritten as s plus 4 squared, and then we had 9 left over. So this then is our, this is the way that looks. And then notice in the numerator, since we have this s plus 4 down here, we want to create two terms, one that contains an s plus 4 and the other that contains a constant. So all this term is it's just this term rewritten. So how would you do that? Well, if I want s to be s plus 4, that would be 2s plus 8, and I would have 2 left over, which is where this 2 comes from. Then we play with that a little more. So the first thing we do is we rewrite the s plus 4 term, and then we had 2 over this denominator that came from here. But what we actually want is, since this is 3 squared, we actually want a 3 in the numerator. So we make this term 2/3, and then we multiply that by 3, so that this is now our constant, and then this is our term in the looking the way we want it to look. So once again, you're doing this for a specific reason. One of the common methods of solution of differential equations is the Laplace transform and inverse transform approach. This is the way you would want to express this polynomial in partial fraction, or this rational function in partial fraction terms, if you're going to apply the Laplace technique. So we're just going to learn that now. in the algebra, so that when we do get to that differential equations part of the course, this is something that you have already seen. All right, so that's going to conclude the lectures on polynomials and rational functions, and we will start up again with exponentials.